Isabel was lying under a pear tree, she observed a pear drop to the ground from about 1.5 meters. Plonk! She reckons it took about half of a second for that drop to occur, and she was wondering if pears higher up the tree, for example the one at 3 meters, here, might take somewhat longer to drop to the ground, and how much longer that might be. Maybe twice the time, or 3 times the time, or somewhat less than twice the time, or maybe the same time as the first pear that she observed. So the question is, how long does it take for a pear to drop to the ground from a tree from 1.5 meters or 3 meters height? That's a problem that can be solved with dimensional analysis. And one does the following consideration. Well, we want to know the time it takes for the pear to fall to the ground. Surely that'll be dependent somewhat on the height from which it drops down. Maybe linearly, maybe not, so we put an exponent a here, height to the power of a. The time might depend on that. The larger the height, the longer the time it takes. That's a sensible argument, and that's the sort of argument you use in dimensional analysis. The acceleration of the planet is a certain quantity that will go into here. If the acceleration of the planet is larger, and we know that on the moon things drop not as readily as on Earth, so if we have a larger acceleration, we'll have a shorter time for this drop to occur. If we have a lower acceleration, we will have a shorter time for this to occur. So acceleration may be also not linearly, but to the power of some exponent b might come into this. It might depend on the mass of the Earth, because not, as we know, because of action equals reaction, not just the pear attracts the Earth, but the Earth attracts the pear, and vice versa. So if the Earth has a certain inertial mass, then that will go into our consideration. And again, this might be to the power of something, let's call it c. And because it's symmetric, the inertial mass of the pear should also go into our consideration. The inertial pear mass, maybe to the power of d. Yeah? The more inertia a pear has, the more difficult it'll be to drop. So the height would be longer, the time would be longer for it to drop down. And symmetrically, equivalently, because of the symmetry, the Earth mass, if the Earth has a large inertial mass, it'll move towards the pear somewhat slower, and that should affect the time for this drop. So if we now combine all these arguments, we find that the time is proportional, the time for the drop, it is proportional to the height to the power of a times the acceleration to the power of b. G is conventionally used as the gravitational acceleration of a planet. G, on Earth it's 9.81 meters per second squared typically. It depends on location. Then the mass of the planet would be m to the power of c, capital M, and the mass of the pear would be little m to the power of d. How can we work out these exponents? Well, this is where we now use dimensional analysis, because we can write that time has the dimension seconds. And we know from our arguments that that time should be proportional to the dimension of height, which is meters, to the power of a times gravitational acceleration, which has the dimension meter per second squared, to the power of b times kilogram to the power of d times kilogram again, in this case for the mass of the pear, to the power of d. And here it should have been c. So we've got m to the power of a, m on the s squared to the power of b, and kilogram to the power of c, and kilogram to the power of d. Now, this has to work out. We have to have the same dimension on the left as we have on the right. On the left we know we have time, so we have the dimensions s. So how do we get from the how do we choose these exponents a, b, c, and d so that we get the dimension s also on the right hand side? That can be done by first realizing that in this case the kilograms should not go in at all, because they don't appear on the left hand side. So therefore C, the exponent C, has to equal the exponent D, and in fact minus D. So we might pick 1 on one side and minus 1 on the other side. Then these 2 kilograms cancel. The second squared here is very useful, because that's what we need. We need the dimension of time, but the second has to go into the numerator. So therefore the exponent of B, the exponent B, has to be equal to minus, to invert the second squared, and we also have to take the square root to get rid of the square. So the exponent B has to be minus 1/2. If we choose B as minus 1/2, then we have a meter to the power of 1/2 in the denominator. That has to be cancelled out by the meter here, so therefore the A has to be chosen as 1/2. The exponent A has to be 1/2. And therefore we can then write down that our equation looks like this. We have S, dimension second, is proportional to meter to the power of 1/2 times meter per second squared to the power of minus 1/2. If we now go back to variables from that, this is a dimensional equation. If we go back to the equivalent variable equation, we have second, that's time, is equal to, we get rid of the proportionality by introducing a constant, which we don't know, times meter to the power of 1/2, that's the square root of the height, times 1 over the square root of meter divided by second squared. So we get constant times the square root of h divided by gravitational acceleration. Here I should have written g. And that would be the result of the dimensional analysis. It tells us that the time is proportional to the square root of the height. So in the case of Isabel, where Isabel observed drop from 1.5 meter with a time of about 0.5 seconds, we can now predict that assuming that the gravitational acceleration is constant in both cases, the pairs, the trees at the same spot, both pairs on the same tree, so gravitational acceleration should not vary. So therefore the time for the drop from, we should write maybe drop from 3 meters should have a time of the ratios of the square roots. So we have square root of 3 divided by square root of 1.5 times 0.5 seconds, and that's equal to, let's type that in, 3 square root divided by 1.5 square root equals 1.4 times 0.5 seconds. That's 0.7 of a second. 0.7 of a second. So you can see, despite doubling the height, we're not doubling the time it takes for the pair to drop.